Let's see nodes and links. Communication at the data link layer is node to node. A data unit from one point in the internet needs to pass through many networks such as LANs and WANs to reach another point. These LANs and WANs are connected by routers. We refer to the two end hosts and the routers as nodes and the networks in between as links. Let's look at this diagram. So already in the last slide we have seen that the source host and the destination host and the routers are termed as nodes. So here the first node is our source host and the last node is our destination host. The other four nodes are the four routers. So here we have four routers, and the first, the third and the fifth links represent the LANs. The second and fourth links represent the WANs. Now let's look at the different services that are provided at the data link layer. The data link layer is located between the physical and the network layers. The data link layer provides services to the network layer because the network layer is above the data link layer. It also receives services from the physical layer, which is below the data link layer. The duty scope of the data link layer is node to node. When a packet is traveling in the internet, the data link layer of the node or the host or the router is responsible for delivering a datagram to the next node in the data path. In this diagram, we can see the difference between encapsulation and de-encapsulation. During encapsulation, a header and a trailer are added to the data and made into a frame. And during de-encapsulation, the header and the trailer are removed and they are separated. The data link layer of the sending node needs to encapsulate the datagram received from the network in a frame. The data link layer of the receiving node needs to decapsulate the datagram from the frame. The data link layer of the source host needs only to encapsulate. The data link layer of the destination host needs to decapsulate. But each intermediate node needs to both encapsulate and de-encapsulate. Now let's look at this diagram to see how encapsulation and decapsulation works at the sending side and the receiving side. In this diagram, we can see at the sending side, at the application layer, we have the data. Then the data moves to the next layer, that is the transport layer. When it moves to the transport layer, a segment header is encapsulated to the data. Now the segment header and the data moves to the next layer, which is the network layer, and here we can see a packet header is added to the data. Now again the packet header, segment header and the data moves to the next layer, to the data link layer. Here we can see a frame header and a frame trailer is encapsulated and it becomes a frame. This frame is converted to zeros and ones and then sent to the receiver side. At the receiver side, the zeros and ones are received at the physical layer, and at the data link layer, now the de-encapsulation occurs or decapsulation occurs. So here we can see the header and the trailer are removed. Now the packet header, the packet segment and the data moves to the network layer. At the network layer, again the packet header is removed. Again the segment header and the data moves to the transport layer. Here again the de-encapsulation occurs and the segment header is removed and only the data is sent to the application layer. The sending data link layer at the end of the link is a producer of frames. The receiving data link layer at the other end of the link is a consumer. If the rate of produced frames is higher than the rate of consumed frames, frames at the receiving end need to be buffered while waiting to be consumed or processed. We cannot have an unlimited buffer size at the receiving side. There are two solutions to this problem. Let the receiving data link layer drop the frames if its buffer is full. Or the receiving data link layer can send the feedback to the sending data link layer to ask it to stop or slow down. Error control. At the sending node, a frame in the data link layer needs to be changed to bits, transformed to electromagnetic signals, and transmitted to the transmission media. At the receiving node, the electromagnetic signals are received, transformed to bits, and put together to create a frame. Since electromagnetic signals are susceptible to error, a frame is susceptible to error. The error needs to be detected. After detection, it needs to be either corrected at the receiver node or discarded and retransmitted by the sending node. Next service provided by the data link layer is congestion control. A link may be congested with frames, which may result in frame loss. Most data link layer protocols do not directly use a congestion control to alleviate the congestion, although some wide area networks do use. The data link layer can be divided into two sublayers. They are data link control, which is DLC, or media access control, MAC. The data link control sublayer deals with all the issues common to both point-to-point and broadcast links. The media access control sublayer deals only with the issues specific to the broadcast links. In the diagram, we can see we have a data link control sublayer and the media access control sublayer for a broadcast link. And when we are dealing with only point-to-point link, we have only data link control sublayer. The other service that is provided by data link layer is link layer addressing. A link layer address is sometimes called a link address. Since a link is controlled at the data link layer, the addresses need to belong to the data link layer. When a datagram passes from network layer to the data link layer, the datagram will be encapsulated in a frame and two data link addresses are added to the frame header. These two addresses are changed every time the frame moves from one link to another. Let us look at this scenario here. Here we have two people who want to communicate. Here we have Alice and Bob. Alice wants to send a message to Bob. Now Alice is connected via different switches and routers to Bob. Here we can see there is one switch, two switch and three switches. And there are two routers. So the network address of Alice is N1 and the link layer address is L1. And the network address of Bob is N8 and the link address of Bob is L8. So let us look at the packet format. In the packet format, in the first part we have L2, which is the destination address. So here we are going to give the immediate destination, which is from L1 to L2. Okay, so this is L1 link 1 and this is link 2. So we are going to give the address of the immediate next destination, which is this switch, and source is L1. So from L1 to L2. And when we give the network address, we give N1, which is the network address, source address of Alice, and the destination address N8, the destination address of Bob. Destination address of Bob is here. So here we can see the message moves from this switch to this switch, and the message reaches here. Then from router 1, the message again goes to the next link, that is L4. So when we look here, we can see the first part we have L5. L5 is the destination link address and L4 is the source link layer address. Okay, and the network address remains the same here. This is in link 2. Next, when we go to the link 3, this is the link 3. Here we have L7, which will be acting as a source, and L8 will be acting as the destination. So here we have L8 as the destination and L7 as the source. And in the case of network address, the network address remains the same, N1 and N5. So here we can see something interesting. When you represent the link layer address, first we represent the destination, then the source. But when we are representing the network layer address, first we represent the source followed by the destination. There are three types of addresses available in data link layer. First one is a unicast address. Each host or each interface of a router is assigned a unicast address. Unicasting is one-to-one communication. A frame with a unicast address destination is destined only for one entity in the link. The unicast link layer address in the most common LAN or Ethernet are 48 bits or 6 bytes, and they are represented as 12 hexadecimal digits separated by columns. Here we can see one example: A3 colon 34 colon 45 colon 11 colon 92 colon F1. The next type of address is multicast address. Here, this type of communication can perform one-to-many communication. Here, the addresses are represented using 48 bits that are presented as 12 hexadecimal digits, and they are separated by colons. And here we can see the example of a multicast address, and here we need to notice that every multicast address, the second digit needs to be a even number in hexadecimal. The third type of address that is available in data link layer is the broadcast address. Broadcasting means one-to-all communication. A frame with a destination broadcast address is sent to all the entities in the link. The broadcast link layer address in the most common LAN or Ethernet are 48 bits, all the ones, and the address contains all ones, and they are represented as 12 hexadecimal digits that are separated by colons. Here we can see one example: FF colon FF colon FF colon FF colon FF colon FF. Now let's look at another protocol that is available in link layer, which is address resolution protocol, or we can call it as ARP. The ARP protocol is used to map a network layer address to a logical link address. ARP accepts a network layer address, maps the address to the corresponding link layer address, and passes it to the link layer. Anytime a host or a router needs to find the link layer address of another host or router in the network, it sends a ARP request packet. The packet includes the link layer and network layer address of the sender and the network layer address of the receiver. Because the sender does not know the link layer address of the receiver, the query is broadcast over the link using the link layer broadcast address. The ARP request is broadcast to all the hosts that are connected to the network. Every host or a router on the network receives and processes the ARP request packet, but only the intended recipient recognizes its network layer address and sends back an ARP response packet. The response packet contains the recipient's network layer address and link layer address. The packet is a unicast directly to the node that sent the request packet. Now let's look at the packet format. The hardware type field defines the field of the link layer protocol. The protocol type field defines the network layer protocol. The source hardware and the source protocol addresses the variable length fields defining the link layer and the network layer addresses of the sender. The destination hardware address and the destination protocol address fields define the receiver's link layer and network layer addresses. The ARP is encapsulated directly into a data link frame. The frame needs to have a field to show that the payload belongs to the ARP and not to the network layer datagram. Let us look at this scenario. Here, Alice wants to communicate with Bob. Alice is the source and Bob is the destination. Here we have N as our network address and L as our link layer address. So we know the source network address, which is NA, and we also know the source destination address NB. We know the source link address, which is LA. We want to know the destination or the immediate destination's link layer address, which is L1. We want to find this. For this purpose, we are going to use ARP. So here initially we have the data, we have the source network address and the destination network address, and we also know the LA, which is the source link address. We want to find out the immediate destination link address. Okay, so the data are filled, or the destination network address is sent to the forwarding table, and uh, and the ARP request is sent to all the hosts in the network, and the particular router. So this router sends back the reply. So here we have R1. So R1 sends the reply as L1. It tells that L1 is the immediate link layer destination. Okay. So L1 address is given back. So now we have the destination link layer address, source link layer address, source the network address, and destination network address. Let us assume Alice needs to send a datagram to Bob. Network layer knows it's given NA, which is the source network address, and NB, which is the destination network address, and the packet, but it needs to find out the link layer address of the next node. The network layer consults its routing table and tries to find out which router is next for the destination NB. The routing table gives N1, but the network layer needs to find the link layer address of the router R1. It uses its ARP to find the link layer address L1. The network layer can now pass the datagram with the link layer address to the data link layer. The data link layer knows its own link layer address LA. It creates a frame and passes it to the physical layer, where the address is converted to the signals and sent to the media. At arrival, the physical layer of the left link creates the frame and passes it to the data link layer. The data link layer decapsulates the datagram and passes it to the network layer. The network layer examines the network layer address of the datagram and finds the datagram needs to be delivered to the device with the network layer address NB. The network layer consults its routing table to find out which is the next node or the router in the path to NB. The forwarding table returns N3. The IP address of the router R2 is in the same link with R1. The network layer now uses the ARP to find the link layer address of this router, which comes up as L3. The network layer passes the datagram and L3 to the data link layer belonging to the link at the right side. The link layer encapsulates the datagram, adds L3 and L2 of its own link layer address, and passes the frame to the physical layer. The physical layer encodes the bits to the signals and sends them through the medium to R2. At Bob's side, there is no more addresses or mapping needed. The signal received from the link is changed to a frame. The frame is passed to the data link layer, which decapsulates the datagram and passes it to the network layer. The network layer decapsulates the message and passes it to the transport layer. In this diagram, we can see System A trying to communicate with System B. System A knows the IP address of System B. So it's looking for the physical address of a node with IP address 141.23.56.23. So it sends the request to all the nodes in the link. All the other nodes reject the request, but only the destination replies with a physical address. The request is given as a broadcast and the reply is given as a unicast.